Thank you. So yeah, my talk is about flammable cities. And the context that I'm going to try and paint for you is a global one. And then we're going to have a look through what the science is and go into then a kind of case study of a research project that started 2 years ago and go into kind of a few of the things that we're learning there and doing there to kind of basically understand the problem. So what is the problem that we're talking about? So urbanization. We have 7.5 billion people in the world currently, of which about 85% live in lower middle income countries. And there's an estimated 1 billion of people in the lower middle income countries that live in things called informal settlements. And that's about 33% of the urban population around the world live in these informal settlements. So here we've got an informal settlement. If you've been kind of out in the kind of foyer looking at some of the things, you would have seen Mohammed and Yu Wang with their presentations talking about informal settlements. This is Khayelitsha. This is one of the informal settlements in South Africa, around Cape Town. Around 400,000 people live in this informal settlement. It's the 5th largest in the world. When you go to Kibera in Nairobi, we get to around about 600,000, 700,000 people living in one informal settlement. So what is I had used two terms there, a lower middle income country and informal settlement. So what is a lower middle income country? So this is a map showing where those lower middle income countries are. And essentially anything from yellow, orange and red, that's a lower middle income country. The blues there are high income countries. So you can see where the kind of global distribution in terms of wealth is being related. And then we've got informal settlements. And this is a term which is relatively kind of globally used. Sometimes you'll hear the word slum or favela or shantytown. These are all kind of other terms that are used in very more local contexts for essentially a settlement that has little or no legal right to be there or very little official planning for its being set up. There might be a couple of roads through there, but all of the more kind of informal streets are very much organically generated. And we've got a problem with urbanization. Our kind of cities are growing at a very quick rate. So here we've got a little GIF looking at the top 20 cities globally by population. And you can see there's a fairly good spread in 2025 or 2015. And as you go through, you're getting a concentration around these kind of African and Southeast Asian cities where, if you think about the slide before, these were low middle income countries. Lagos, for example, by 2100 is going to be 88.3 million people. That's a single city. Yeah? So 90% of the growth around the world is going to be happening in these African and Southeast Asian countries, and we're adding about 70 million persons per year to the urban environment in those countries. So we're going to look at kind of what that looks like for some specific cities. So we look at Manila. So currently around about 13 million. By the time it gets to 2035, which is only 15 years away, we're getting around about 18 million. If we look at Lagos, about 12 million, up to about 25, so that's doubling, essentially, over the next 20 years or so. Kuala Lumpur, slightly slower growth. If we then look at Nairobi, we've got about 4 million there, up to about 6 million. And then if we look at Edinburgh, pretty much a flat line on that graph. So we're looking at total population in years here. We then look at kind of the idea of percentage change from the 2015 population. Even Edinburgh is going to be growing at kind of 20% over the next 20 years. We can see that around the south of the city. You see the big kind of settlements being there. But within the global north, we've got the ability to kind of manage those developments a lot better than we do potentially in these other lower middle income countries. Kuala Lumpur is actually a special case. They've actually done really well in managing this. And the growth that they've got there is actually going to be fairly well sustained and developed. So that's urbanization. So that's kind of what's going to be happening to our world over the next kind of 50, 100 years. I want to now talk about the global fire consequences. So fire is a big issue within these settlements, and it happens around the world. So this is the kind of death rate, if you want to talk about it. So we had lots of talk about life and fertility from Evelyn. I'm going for the other end of the spectrum and talking about death. So around about 180 to 300,000 people a year die because of fire. When you consider kind of the average loss of life to other natural hazards, that's around about 90,000 people a year. So we're about double the amount of people die in fire every year than you would have from natural hazards. And 95% of those deaths are happening in low and middle income countries. And if we take a look at the UK, in terms of death rates, we've got about 0.3 people per 100,000 dying a year, where in the likes of the Ivory Coast, that's 14.3 people. So it's around about 50 times more. And then we think about disability. So a consequence of fire is not just necessarily death, it's also about morbidity. You might lose a limb or be scarred from both psychologically and physically from fire. And there's around about 10 million disability adjusted life years lost. So that's what a daily is, a disability adjusted life year lost every year due to fire. So fire has a massive consequence to people, but it also has a massive consequence to the global economy. So the cost of fire each year is about 1% of global GDP, which is about 800 billion US dollars, or half of the GDP of sub-Saharan Africa. So it's a massive consequence. Fire costs a lot of money, but it also costs a lot of other consequences. And when we consider where these high areas are and consider where the lower middle income countries are, we can switch between those two graphs, and you can see they correlate pretty much exactly with the highest death rates being within this sub-Saharan Africa, and this is where the lower middle income countries are. So this is a real issue that we're trying to tackle here at Edinburgh. And I want to kind of focus a little bit more on who's actually being affected the most. So I've got global fire consequences of the younger. So deaths in terms of 0 to 14-year-olds. For high-income countries, it's 0.4, which is about what the average would be for everybody. But when you get to lower middle-income countries, you're at 10 times that, 4.3. When you're thinking about disabilities in high-income countries, it's about 50,000 disability life years lost. When it comes to low middle-income countries, about half of that 10 million dailies is attributed to the 0 to 14-year-olds. So it's a massive issue for our young. And it's an issue because they're the ones that don't necessarily have the education or the ability to actually move out the way of a fire. They don't know what to do. And the other consequences of there are kind of a loss of education, employability. So if you're scarred, you may not be able to go to school because you might be teased, you might have social interaction problems, which then impact your ability to actually earn money and get out of that problem. So it's a massive issue. And I just want to highlight kind of 4 fires for you, which have happened over the past kind of 7 or 8 years. These are just 4 big fires, but there are thousands, if not millions more fires that happen globally. So in 2011, we have Bahay Toro in the Philippines, where in a single fire which burnt for 5 hours, 10,000 people were made homeless, and there was only 1 life lost. So we're not thinking here that we're losing huge numbers of people in a fire, but we're impacting hundreds or tens of thousands of people. The same here, we've got 2,500 homes in Valparaiso. This fire burnt for 44 days. It started in an informal settlement, it moved up into the forest, the wind changed direction, and it moved back down into another settlement. We have Imazami Yeto in March 2017. Here we had about 2,100 homes destroyed, almost 10,000 people displaced because of that. 4 dead, it burnt for 13.5 hours. They ended up having to bring in helicopters to drop water on the fire to stop it spreading into the nearby forests and velds. And then in January 2018, we've got this fire in Kijiji in Kenya, where we have 6,000 people made homeless and 5 people died, and it lasted for 8 hours. And the big takeaway from this fire is that they had a lack of water. There wasn't enough pressure within all the pipe works because of the dry season to actually put out the fire. So when it comes to things like global warming, this problem is going to actually start exacerbating in our settlements, which are going to be growing as well. And it's not just kind of the people who are choosing to move, but it's also those who are physically displaced. So the Rohingya, in October last year, we had 6 dead and 12 structures destroyed, leaving 900 homeless. Those structures must have been housing a lot of people. And then in Lebanon, we have 1 million refugees living there, mainly from Syria. We also have some Palestinian refugees. And when you think about children, which are about half of the population of the refugees from the Syrians, their death rate is up at 20.6 per 100,000 per year. So this is even higher than Côte d'Ivoire, which I showed you on the map earlier, being 14.3. So I think we have a duty as other human beings to actually start looking at this more seriously. But the good thing about these people is they are resilient. So when the fire does happen, say in South Africa, fire happens one day, they will rebuild their homes the next day. They will be getting back on with work. And it's this idea of resilience, which I really want to kind of, it's the frame within which the work that we're doing here at Edinburgh kind of sits. So we have this is an engineering example of what resilience is. And resilience is just the ability to recognize, sense, adapt, and absorb variations and changes, disturbances within your environment. So this is a engineering visualization of what we think of as resilience. So we have functionality on our y-axis and time on our x-axis. So we have this idea of normalcy. This is what we ideally want to be operating at. This is what our everyday idea of resilience, of kind of operational functionality is. And then we have a damaging event. This could be anything. This could be an earthquake. It could be a fire. It could be a water pipe in your home breaking. You know, that would all be termed as a damaging event. And we have a loss of functionality. And that loss of functionality happens over a period of time. And then at some point, you'll have a minimum amount of functionality left. And we would kind of call that your residual functionality. Obviously, we don't want to stay there. You know, we're not operating at full functionality when we after the damaging events. We have this time lag before we can get back to normalcy. And obviously, when we think about fires, those large fires are a big shock to the system, where we have a big dip in functionality for that community. But we also have lots of little fires, and those are kind of stresses on the systems, where this drop is actually a lot shorter, and those kind of things happen more regularly. We do have losses of life in those things and belongings. Things like official documents. So if you're trying to go and get money from the state, if you've lost your documents, that's going to affect your ability to function as a member of that society and community and your family. So these little fires actually can have quite a significant loss in functionality for those who are affected by them. So when we're thinking about these kind of regular fires that happen in these communities, so I've shown you the big fires, but these little fires happen regularly, and I'll show you later on about what happens in South Africa, in Cape Town. These urban fires can be defined as something called an extensive risk. So we have an acute risk with things like your earthquakes, your tsunamis, your kind of floods. Where we have an extensive risk, this is a repeated and persistent hazard that kind of continually affects and impacts those around them, and can have a kind of cumulative effect. So fires we can kind of term as this extensive risk, which is stopping people from actually working their own way out of poverty. So what's the science behind kind of the fires? So I've kind of given you the context there of what urbanization is, what resilience is, but I want to kind of take us back to actually what a fire is. So hopefully you all know what this is. Yeah, this is a match. And we have fuel in that match. So the stick is the fuel. We have a bit of accelerant up here, but the stick is the fuel. It will be kind of impregnated with a bit of flammable liquid as well. Most matches are, but that is our fuel. And it's in air, which has got lots of oxygen in. So what's the last thing that we're missing to get a fire? Heat. Brilliant. So we add in some heat, and it ignites. We have a little fire. You can see kind of the moisture there moving, and we've got some kind of charring, and we've got this flame. What's actually happening? So let's look at that in a bit more detail. So here is our fuel. It's in air. We've got some heat exposed to it, and we get a fire. So the first thing that's happening is when we have that heat putting onto it, is we're having something called pyrolysis. This is the thermal decomposition of the material due to heat. And what's that doing is that is creating volatiles. So these are kind of combustible molecules which are being kind of pushed up because of the heat, the buoyant air, as a fuel. And this is kind of in a gas form. And as you'll see, kind of, we've got some color up here, but we've got no color up down here. And this is where the air is being entrained into the fire. So we need oxygen, we need heat, and we need fuel. So we've got fuel being pushed up through pyrolysis. We've got heat from their inherent heat, and now we've got oxygen and air coming in from the air being entrained. And this is where our fuel reacts. This is what the fire is. And what happens to kind of that fuel? When it reacts, it creates a lot of energy. Where does that energy go? So we've got energy being kind of lost in gas form, upwards into kind of the ether. Yeah. So if I was holding a match here, none of you would feel it. Yeah. And all that heat would just be being lost and dissipated as energy into this room. We have energy being lost as radiation. So that flame has got a lot of energy. It's then kicking out that energy as radiation. And what does that radiation do? Well, it feeds back into our fuel to start turning this fuel through pyrolysis into a gas, which then can be burnt. There's also another heat transfer mechanism that's happening in here, which I haven't spoken about, and that is conduction. So we've got heat here from the fire and from the pyrolysis. This is hot, and that heat, that energy is being transferred through the material. And those two activities of kind of the radiation back to the fuel and the heat conduction, that continues this pyrolysis loop that's happening. Okay, so that's a match. What happens when that match is within a compartment, a room like this, for instance? Yeah, if that match was on one of your chairs that you were sat on. Okay, so we've got our room here, which is this kind of green block. We've got a couch, we've got a bit of carpet. Here we've got a bed, some shoes, curtains, a lampshade, typical student digs. And we have an ignition. Yeah, so this is someone putting a match carelessly onto the arm of their couch. Yeah, and so I've got a graph here, which is looking at the heat release rate, or the energy being released with respect to time. So in this early stage, not a lot of energy is being released. So you've got a very small amount of energy being released from that fire. But that fire has kind of started that combustion, that pyrolysis of the materials really close to it. And so we start getting a bigger fire. That feedback is happening to the localized materials. And we start getting a bigger fire. So we have more energy being released. And we have kind of those two heat transfer mechanisms happening again. We've got radiation and we've got conduction. But we've also got a difference there. So we've got a slightly larger fire here than our match. And what's happening is all those hot gases are starting to be caught at the top of the room. Yeah, they're not being allowed to escape. That's going to play a very important role in a few slides' time. So we've still got that fire, but it needs air. It needs oxygen. So we've got this air flow coming in to the room. Yeah, and that is helping to drive the hot gases up, and that's why we have this slight tilt in our smoke. If it was in a nice big open space, we'd have a nice symmetrical plume going up, a nice kind of conical shape. But when you start adding it into a compartment where you have a restricted amount of air coming in, that plume starts to be kind of pushed towards that back wall. And in this case, that would be pushed toward that curtain. So that's going to be another kind of fire spread mechanism. And at this point, there's enough air within the room to sustain the combustion that's happening on the couch and on the sofa there. But that starts to build up. We're getting more energy being released by the fire, start spreading to more things through that kind of conduction and radiation. So we get this faster flame spread. And you can see here is we're at this kind of transition stage where we're going to start getting a very rapid increase in energy being released from the fire. And that's something called flashover. So this kind of period here, some people have it as a specific point. I prefer to have it as kind of a period where we're starting to get a lot of radiation feedback from this hot smoke. So this hot smoke, we've got some combustion happening in it, but in itself is hot. And things that are hot will radiate heat. Your radiators aren't on fire, but when you go close to them, they are radiating heat. So this is kind of one of the key feedback mechanisms for a flashover. And what happens is when you get all this radiation, it's not just the fire that's being kind of radiated to, it's all the materials within that room. So your carpets, your trainers, they're starting to pyrolyze. They're starting to release those gases. That's what you're seeing kind of in that kind of white smoke there. That's the kind of pyrolyzing material that hasn't yet caught alight. And you get to the kind of this fully developed stage where you've got a fairly regular and consistent amount of energy being released by the fire. And that's where the fire that's happening inside this compartment is now being limited by the amount of oxygen that can come in. So we have this hot layer of gases being thrown out, and we've got this cold layer of air coming in. And we have this idea of neutral plane. This is a fairly regular and consistent thing that we can kind of predict with our models, depending on how big the opening is. So we can actually start understanding very, very regularly for these kind of very well-known compartments like your rooms in your houses, where this kind of neutral plane is and how this will react. And we then, once the fuel starts being burnt up and kind of there's less and less of this material to actually pyrolyze and turn into gas and burn, we get this decay phase. So that's what happens in a room. So if you imagine one of those informal settlement dwellings that I showed you in the first slide, that's now caught on fire. How does a single compartment fire spread from one to another? So imagine this is kind of our single dwelling being on fire. And I'm going to give you an example using trees. So the stuff that I'm talking about here is very common in wildfire scenarios. And we can have similarities and similar thinking when we start thinking about informal settlement fires. So the first thing that we have is we have those hot gases being released. But we also have these things called firebrands. Now, I know that Mohammed's and you's kind of talk, there are a few kind of questions talking about firebrands, and I heard a couple of questions asking what a firebrand is. So if you imagine your bonfire, all these kind of traces of orange up here in a time lapse, those are firebrands. These are little things, the little glowing embers that get kicked off a fire and get carried up in the smoke. Now in a bonfire, you've got a small fire, those will go maybe 2 or 3 meters. When you've got a forest fire, they can be transported hundreds of meters, if not kilometers, depending on the wind and things like that. So those little embers can actually start more fires. We've also got radiation, and we've also got direct flame contact. So if one of these 2 trees was on fire and the branches were overlapping, that would spread the fire from one fuel package to another. So at the moment, we've not got any wind in this picture, which is a key driver for fires. So if we add some wind in, our firebrands get kicked off at a different angle. So these can now spread a lot further. Instead of just going straight up and kind of falling nicely down in a nice plume, these start getting blown by the wind that can be transported, as I said, kilometers. And also our flame contact region also gets tilted. And so these are the main fire spread mechanisms within informal settlements. We have firebrands, radiation, and direct flame contact. And that's the same as you would find in wildland fires. So what are we trying to do about it at Edinburgh? So as I spoke about, we're trying to understand the current resilience. So we've got this project called Iris Fire, which is about improving the resilience of these informal settlements to fire. It's an interdisciplinary approach because fire is as much a social construct as it is a physical one. It is a man-made hazard. We try and control it. Some places we're good at it, some places we're not. So we're trying to understand both the socio-political engineering issues as well as the kind of topological and geographical issues surrounding fire. And so we've got this idea of trying to improve this idea of resilience. So we're looking at kind of fire spread in these informal settlements like we would for forest fires and wildfires. But we've got key differences. We've got a key difference that in informal settlement fires, we're very close to life. We've got very different characteristics of fuel. In forest fires, it's all cellulosic, very nice, easy. looking at all the fire colleagues in here who are giving me glares there when I'm saying it's easy. We've got a fairly regular kind of set of parameters compared to some of the fuels that we have in informal settlements. And we have very different management strategies. So our aim in Iris Fire is to kind of provide this database and information so that policymakers and people who are interacting in these areas can actually really affect change. So Iris Fire is at the moment in Cape Town and looking at South Africa. And the reason that we're there is it's one of the most unequal societies around the globe. It's got luxury apartments right next door to informal settlements. We've got around about 33% of the population living in informal settlements and in backyard dwellings. So one of the interesting things that we see in South Africa is that we have social housing being provided, but the people being put into the social housing are at the lowest end of the socioeconomic spectrum, which means that they can't afford to maintain and upkeep their homes. So what they do is they build informal dwellings in the back garden, rent out the home and live in the informal dwellings. Yeah? Or they live in the home and build several informal dwellings and rent those out. Yeah? Just so they can have that property in that space. But the good thing about Cape Town is that we've got really good fire statistics. We have about the same number of fires in informal settlements as we do in formal areas, which means that an informal dweller is about 3 to 5 times more likely to experience a fire than someone who's living in a more luxury accommodation. We have a good frequency of fire, so anecdotally we have a fire every day in informal settlements in South Africa, in Cape Town. And we have a fire that will affect more than 20 dwellings at least once a week on average. Yeah, so if you imagine a city having a fire that destroys 20 homes every week, that's quite a big problem. And we've got ignition causes that vary across that. So they could be cooking, as we would find in the UK. Kitchen is the most likely place that your fire is going to start. But we also have electrical faults and surges. We have arson. We have children playing with fire, just to kind of have something to do. In terms of fire deaths, at the start I was talking about kind of these differences in South Africa, so not in Cape Town, but in South Africa, we've got 374 under 5s dying each year, which is a death rate of 6.3, and 274 over 70s, which is 14.8 deaths per 100,000. We compare that to the UK. In 2013, we had 2 under 5s dying, and we had 117 over 70s. So when we kind of start thinking about kind of the impacts on low middle income countries and within South Africa, children are potentially kind of 11 times, probably more like 7 times more likely to be affected by fire. So I just wanted to kind of highlight these total fire deaths and these rates for these two kind of populations, the very young who don't know what to do and the very old who aren't necessarily capable of moving out the way of the fire in time, because these things spread quickly, as I'll show you soon. So what are we trying to do to understand it? Well, we're looking at informal settlements. So these are some of the pictures of Imazama Yetu here and Matupumelele. And as you can see, this is not an atypical spacing between homes or an atypical egress route if there was a fire. So this kind of shoulder width between dwellings is very common within these settlements. We've got dense settlements of buildings made with steel roofs and timber frames, timber or steel walls. We've got plastic sheeting in there. We've got cardboard and low density insulation. So in Cape Town, it can get to about 7 or 8 degrees, commonly during the winter, and around about kind of 35 during the summer. So these homes, they need the insulation to make sure that their internal climate is survivable. But it causes a massive fire risk in terms of fire spread. So what are we doing? We're doing these surveys. So we're doing these kind of qualitative, systematic surveys just of not only of the social political structures, so that from top down, how are these areas being governed, but also from the bottom up, how do the inhabitants think about fire? How do they think about fire spread? What's their experience of fire? What are their risks that they see within their settlements? And we're trying to understand what the inhibitors of kind of this self-protection are. Is it money? Is it policy? Is it the fact that their neighbours don't want them to build brick walls because it means that, those sort of questions? And what are the perpetrators of fire hazard? We're also doing quantitative surveys where we're looking at stochastic topological data. We're trying to understand what this is in a general sense. We're not looking at individual homes. We want to understand in a kind of probabilistic, very statistical way, what do these homes actually look like? So we've got, the widths, the lengths, the heights. These vary greatly. How they're made varies greatly. How many windows, doors, what type of insulation they have, what's actually in the homes, how many mattresses, how many sofas, whether there's a fridge or a freezer, all play a really important role in terms of us understanding what their homes are, but also the fire risks. We're doing lots of experimentation. So this is small scale stuff. You would have seen some of these samples upstairs. We've burnt these kind of 400 odd times last summer to understand kind of what are their key ignition and fire contribution characteristics. And we're also looking at medium scale experiments where this is a quarter scale kind of home that we can experiment on in our labs to understand some of the more basic and fundamental dynamics. We're then looking at full scale experiments. These are fires sped up 8 times. Don't worry, this is not the real speed. But you can see kind of this is a single dwelling and then we've got 2 dwellings. So here we're trying to understand the fire dynamics within the home and kind of really understand how things progress. So you can see up here the wood and cardboard catching, and we get a very quick flashover of the cardboard, and then it dies away as the volatiles that are in there have been consumed. And then as the timber heats up and creates more volatiles, we'll get a second flashover. So this is a really interesting thing that we're seeing within our experiments. We're getting this idea of double flashover. And here we've got fire spread from this dwelling which was ignited first, and then you can see the top of the dwelling where all the hot gases are has started to ignite. That starts spreading down the cardboard lining that's in the inside. We'll get a cardboard flashover happening any minute now. There we go. That will die away. And then the wood inside starts to again pyrolyze, and we get that second flashover that we see. So we're looking at both a single unit and then also the fire spread between the 2 units to make sure that we are understanding the science as much as we can. And we're doing this not just within labs, but we're also doing it outside. So here we have 12 dwellings with the wind. So the fire was started the furthest away on screen in those 2. So we're trying to see how the fire spreads against the wind. Yeah, how much effect does the wind have? This is the same experiment, but a lot later on after. So this dwelling here is this one here. It didn't catch, so we set it light, and the wind had changed direction. And as you can see, the wind really extends those flames out of the homes to kind of 3.5, 4 meters in sort of length. So if you're thinking about the direct flame contact fire spread mechanism, if your home is within 3 or 4 meters, you're in trouble. And then up here, this is sped up 4 times. We set a light to these 4 dwellings at the start, and we wanted to see how the fire would spread. So the wind is coming from this direction, as you can see from the smoke. And so these 4 catch, and then quickly the next 3 catch, and then it's a little bit slower up here. But this is 20 dwellings. From the start of the time that we ignited this fire to all the dwellings being caught alight, all 20 dwellings, was 12 minutes. Yeah. So, and this was not with a strong wind. This was about, I think, 10 kilometers per hour. Yeah. So about 6 or 7 miles per hour. A gentle breeze. So even a gentle breeze can cause this very rapid fire spread in these sort of dwellings. So we're taking all that information from our experiments, we're plugging it into computational fluid dynamics modeling, where we're kind of looking at how the fires develop, making sure that we can understand our experiments, replicate our experiments, so we can then do lots of parametric studies when we start changing the number of windows, changing the size and the shape, different types of fuel within the homes. And we're also looking not just in kind of that, but also a lot more globally. So we're looking at kind of remote sensing techniques. So this is change detection, trying to understand where there might be areas where we don't have good fire statistics, whether we can actually detect fires using, say, Sentinel-2 satellite data. So we're looking at the reflectance of the surfaces of these roof structures. You can see here, so this is 10th of November, 30th of November, 3rd of December. So there's a fire in between these two. A large area was kind of destroyed, and then very quickly the whole settlement is rebuilt. And we can detect that through remote sensing. And we're also looking at spatial metrics. So this was taking some data from the city of Cape Town, digitizing all the roofs, and then looking at how close, how often is one of those roofs the closest roof to another roof. So the blue ones here are the ones at the most risk. They are the nearest neighbor to another dwelling 6 times. So if one of those 6 ignite, you're the next nearest one to ignite. So in terms of the next and future steps, we're doing more experiments. We're analyzing a lot of the survey data that we're looking at, and we're continuing to have conversations with policymakers. So the aim of this project is to speak to policymakers, and also we're talking a lot with the NGOs that work within these communities. And we're also expanding the reach of this research. So this started in Cape Town in South Africa. We're now working in Nairobi and in Brazil. They're kind of firm ones that are happening now. We're starting collaborations in Costa Rica, Chile, South Sudan and the Lebanon, and also in India. So these are the areas where we see the issues on the lower middle income spectrum. So to kind of conclude, I've run over time a little bit, so I think you'll forgive me. We have this massive risk when we think about urbanization and our low middle income country partners. Fires are going to continue to happen. They're not going to stop. In the UK, we have very good fire regulations. We still have 235 deaths a year due to fire. And it does affect hundreds of thousands of people each year. Those in informal settlements don't really have an easy means to protect themselves, so we need to think about the science to do that, whether we can do those kind of large-scale changes. And we also kind of want to make sure that we're protecting the younger generations and also the older generations who are at higher risk from these fires. And we also want to make sure that when fires do happen, that we have ways and means and ideas to actually help them build back better. So they don't build back in exactly the same way, not change their risk profile, that actually they can build back better and reduce that risk. So I just want to say thank you. There are people here, Yuang and Mohammed, who do a lot of help. Well, they did most of this work, to be honest. I just get here to present it. But we've got partners in South Africa, Richard and Antonio. We've also got partners, Leslie, who works here as the geographer. And we're supported by EPSRC and ESRC through the Global Challenges Research Fund. So, yeah, thank you very much.
Yeah, you didn't comment on it, but when looking at your fire deaths, you couldn't help but notice that Russia has extremely high level of fire deaths, but it's not a lower middle income country. So what's the story there? Is that just the cold?
I'm not entirely sure why that is. We have some colleagues from Russia who might be able to help answer that afterwards. It is an anomaly within that data set. It may just be that they report fire deaths and fire injuries in a different way compared to other countries. So how you get classified as being killed by a fire compared to being killed by a burn injury later on differs from country to country. There's no universal kind of thread on that. So it might be because of that.
So yeah, obviously the Grenfell killed 93 people in our country recently. And I was just wondering if there was much data kind of investigating the differences in between the experiences of fire in between different socioeconomic groups in our country, because you spoke about that in Cape Town.
Yeah, so there are lots of parallels here. So the people who unfortunately lost their lives in Grenfell were more social housing. So there is a fire justice issue that we do see. So those who can afford to protect themselves do, and those who can't, unfortunately, are forced into being at higher risk. Grenfell is a very specific case within that, but we see parallels across all the different spectrums around the world, where those with money are safer than those without.
And do you think it's changed anything? Because I know there's still lots of very similar council housing that has the same cladding? Like, do you think from your sort of body of research or anything has changed much?
So yeah, I think there has been a change. There's an awareness now, which there wasn't beforehand, which is a massive issue. Those buildings where the cladding is still there, there's funds to actually help them manage that risk, whether it's kind of taking the cladding off or having a 24-hour patrol to kind of ensure that if a fire does start, people are evacuated. There are changes in policy in terms of the fire services and how they deal with high-rise fires. And there are also changes in the way that we construct buildings and improve buildings. So there are changes. It is slower than it should be. I don't necessarily agree with all the changes. Climate change, for instance, like banning the materials carte blanche is probably a bad idea in terms of climate change because it means we'll produce more CO2. So it's about actually understanding how we manage the risks of other hazards within our environment, which is the key.
For centuries, Caribbean countries have dealt with hurricanes by just rebuilding totally insubstantial buildings that are unable to deal with hurricanes. And so the same thing happens time and time again. So, dare I say it, your presentation was gripping, but don't you think you're actually on a sort of a hiding to nothing? Because it basically comes down to money, and they're just going to build these same kind of shanty towns, and the same thing is going to happen. And not even in it, I mean, in this country as well. You know, people are going to drop a cigarette, and there's going to be a fire.
Yep.
So how do you think you can possibly, I mean, I guess you can set out the facts, but...
So the aim isn't to solve the problem. We're never going to solve fire as an issue. We're always going to have fire-related instances. The aim of the project is more to understand what happens and also trying to mitigate the effects. So when it comes to, say the hurricane example, are there small things that they can do to limit how far that damage goes? Or, you know, can they build permanent foundations but build lighter structures up top, which means that when it comes to rebuilding, it is quicker. They can get their lives back rolling together a lot faster. So it's not necessarily about stopping the impact and the damaging event. It's about making sure that that damaging event doesn't have consequences which are too far down the line.
Very much. Thank you. The informal, and a follow-up from the last question or comment, clearly the informal settlements don't have any regulations or any, you know, there's no policy there. So again, it's, you know, you might find out that if you say you have the foundations or a different material, how do you implement that without some other change in the governments? And
so this is why we're looking both top down and bottom up. So a lot of these settlements are organic and kind of ruled within themselves. And so if we can get in within those structures and understand how they operate, we can influence the change there. So we can say, you're not going to build right next door, you're going to try and make sure that this wall doesn't have cardboard lining on because it's going to set your neighbour alight. And if everyone does that, then actually that could really help protect that environment. And that's not a regulation top-down effect, that is a community, working with the community and working with them to actually make that change. We're also trying to understand the top-down to say, what can we do in small changes to affect the fire issue? And that might be saying, we can relocate a few homes with the community's permission and working with the community, put a road through which is 3 meters wide. We're gonna create a fire break, which both stops the fire from spreading, but also allows firefighter access.
sure, thank you.